Nice to meet you. My name is Jong Lee from South Korea. And I'd like to talk about the phototech and SQISign today. And this is a joint work with Ha Dong-hye, Kim Yeon-hak, Kim Gyu-sang, Kim Suri, Kim Hee-seok, and Hong Seok-ki. Let's begin. These are the contents. Let's begin with the SQISign in a nutshell. SQISign is the only isogeny-based digital signatures in the candidates of the NIST standardization process. It's the Fierce-Shamir heuristic type and has the most compact keys and signature size. And it exploits the Duran correspondence, which is the categorical equivalence between the word of the elliptic curve and the word of the quaternion algebra. For example, the J invariant of the supersingular curve corresponds to the maximum order in quaternion algebra, and isogeny corresponds to the integral ideal. From now on, I just say the integral ideal, just an ideal. Okay. And the degree corresponds to the norm of the ideal. For key generation, the SQISign generates the random secret key, the random secret isogeny, and the corresponding ideal is generated. Then it outputs the public key EPK as the public key and secret ideal as the secret key. Because it is the Fierce-Shamir heuristic, it consists of the three parts: commitment and challenge and response. So the commitment phase, the SQISign generates the commitment isogeny, and then the corresponding ideal is generated. Then by hashing the message and the commitment curve, it generates the challenge isogeny, and the corresponding ideal is computed as follows. The reason why the ideal is computed from, firstly from the O0 is because the all knowledges of the ideals and order structure is from O0. And in response phase, it generates the response ideal first by multiplying a secret and commitment and challenge ideal and turn it into the equivalent ideal with the smooth norm because of the secret reason. And it translated into the response isogeny sigma. And the output is the set of response isogeny and two hints. This hint is about for a verifier to recover the challenge isogeny in the verification process. So in the verification process, verifier recovers the challenge curve from the response isogeny sigma and recovers the commitment curve E prime using the torsion information made deterministically from the challenge curve E and the hint from the signature. And lastly, she checks whether the verifier generates the challenge isogeny correctly by using the torsion information made from the commitment curve E prime and the second hint and the hashing of the message and the commitment of E prime. So because it is the Fierce-Shamir heuristic, we can think of the two types, deterministic SQISign and the randomized SQISign. Actually, although the randomized SQISign is only described in the specification. For the deterministic SQISign, the commitment isogeny is generated by hashing of secret key and the message, which means that when we query the oracle several times with the same message, it generates the same signatures. On the other hand, when you for the randomized SQISign, the commitment isogeny is generated by using a random number, which means when we query the oracle several times, it outputs the signatures always differently. So what is fault attack? Fault attack is the invasive version of the side channel attack, where the attacker injects fault into the security oracle by voltage, electromagnetic, laser, software-based something like it, and inducing the faulty output from which the attacker can extract the secret keys or secret informations. If someone asks me that the photo attack is the photo attack that serious, then what I can say at least is you need to consider if you want your scheme to be realized in the real world. And the NIST has announced that the resistance to side channel attack is one of the additional security properties for standardization. And many researchers have been done on a fault attack on PQC, mostly on lattice-based and secondly on isogeny-based. So we will use two types of fault attack. One is randomization and the other is loopable. Randomization is what it sounds like. It is an attack that the attacker inject the fault into the at the moment of the processing input or the copying situation, making the variable a random number. And the loopable is similar. The attacker inject fault into the iterator of the for loop and making it a random number. Then with a high probability, the faulty iterator doesn't hold the for loop's condition and it aborts. This is the loopable vulnerability. And there's a concept of nth order fault attack. When the attacker inject fault n times during one operation in the oracle, then it is called the nth order fault attack. And in this talk, we will use the first order and the second order. So everything all we need is done. Let's check about the false vulnerabilities we found in SQISign. First one is loopables while computing the commitment isogeny. Computing the isogeny is performed using the for loop. And the operation for each kernel, E and its twist, involve two nested for loop. But they use the single continuous index I. And when the attacker inject fault into the commitment curve, then he can induce the faulty commitment curve with a lower degree. This is the loopable vulnerability while computing the commitment isogeny. And there's a randomization vulnerability while generating the commitment ideal. When the ideal is generated, there is a checking process that whether the generator is primitive in or zero. This can be realized by using the Gaussian elimination, and in Gaussian elimination there is a copy function. Then the attacker can inject fault into the copy function. What we prove in the paper is that we can make by injecting fault into the generator, we can make commitment ideal to be O0 with the probability only depend on degree of the commitment isogeny. And this is the upper bound and lower bound approximation for each security level. And we simulated the fault attack 100,000 times, and it checked it supports our approximation. Okay, let's get into the attack scenarios. My goal is to connect the starting curve and the public key curve via isogeny, which is equivalent secret key. And the fault injection into commitment process to make it brute forceable. But there's a one problem. The attacker cannot recover the isogeny from the faulty challenge curve to the faulty commitment curve with the given information after the injection. Why does this happen? I'll give an explanation with the examples of fault attacks and deterministic and randomized SQISign. Before that, we have to give an assumption on attacker model. Attacker is allowed to make the multiple queries to determine the SQISign with the same key. And the oracle generates the signature for each query and the attacker receives it. Then the attacker can inject a fault once during the oracle's operation. This is called the first order fault attack. So this is the path. This is the normal behavior. And when first order fault is injected while computing the commitment isogeny, the faulty commitment isogeny has a lower degree, but the commitment ideal remains the same. And the data flow goes like this. What we have to focus on is the codomain of the faulty challenge curve, and the codomain of the faulty response curve is different. And this is what the attacker can get from the faulty signature. He cannot recover the faulty commitment curve, nor the normal commitment curve. So it becomes unknown. So she thinks for a while, and she realizes that she can use the normal signature with the same message. This is how it works. First, the attacker queries the signing oracle with the normal execution. Then second, the attacker queries the signing oracle with the fault injection inducing the faulty commitment curve close to the commitment curve. Then the attacker brute forces to find the isogeny between the commitment curve and the faulty one. Then how can she check whether the guess curve is right or wrong? If her guess is wrong, then the information made from a wrong curve makes a wrong isogeny. Then the push faulted isogeny goes to somewhere. But if her guess is right, then the right information made from a faulty commitment curve make a right isogeny, and it goes to the codomain of the real response isogeny sigma. By repeating this process, she can recover the entire commitment isogeny. Then she gets the isogeny from starting curve to the poly curve, which is the equivalent secret key. When the degree of the commitment isogeny is B smooth, the total number of queries is all log of the degree of the isogeny, and the time complexity is OB times log of the degree of the isogeny. How about the randomized SQISign? The difference between the randomized one and the deterministic one is that in this case, we use the randomized oracle, and the attacker can inject twice during one operation. So we inject the fault, the first fault in the commitment isogeny and the second fault into the commitment ideal. Then it makes like this. The left one uses the left one uses the loopables and the right one uses the randomization vulnerability. And the data flow goes like this. And you can see here is the same thing happens. The codomain curve of the faulty challenge isogeny is different from the codomain of the faulty response isogeny sigma. Then she has to think the same question in the previous slides and realize that she can use the we made an identity map in the O0. Okay, this is how it works. First, the attacker queries the signing oracle with the second order fault injection, causing the faulty commitment close to the starting curve and commitment ideal to become O0, which is an identity map in the world of the elliptic curve. Then the attacker brute force to find the isogeny from the starting curve to the faulty commitment curve. So in this case, how can she check whether the guess curve is right or wrong? If her guess is wrong, then the information made from a wrong curve generates the wrong isogeny, and it goes to somewhere else, a random curve. But when her guess is right, the right information from a faulty commitment curve generates the right isogeny, which then the push forwarded isogeny goes to the codomain of the faulty sigma. Then she immediately gets the isogeny from E0 to the public curve, which is the equivalent key. So with the same situation, the total number of queries takes O cubes of decom over phi decom by theorem 2, and the time complexity takes OB. So conclusion, we found 2 fault vulnerabilities in SQISign and showed the key recovery attack scenarios on both deterministic and randomized SQISign using this vulnerability. And both vulnerability can be countered using the intuitive method that checking the iterator and the norm has expected size at the end of the computation. And when you consider for the high order fault attack, you have to consider, you just add the checkers. You add more checkers to check iterators and norm is right or wrong. Thank you.
Thank you. Does anybody have a quick question? And so we are going to reach time for break. Anyone? All right.
Hi, thank you for the lovely talk. When it comes to more traditional side channel attacks, there are countermeasures like masking that can prevent them. What countermeasures exist at that kind of level and generality for these fault attacks? How best should schemes be designed to avoid these kinds of fault attacks?
You mean the general method to countermeasure the fault attack?
Yeah, or either that or particular to SQISign.
Actually, the loopable vulnerability can be countered by using the multiple checkers. And the full randomization is based on the circumstances, because in an LWE, it is not like this logic. So it's a different area. So you have to think each cases in that case. And for power analysis, there is a general way to countermeasure the side channel attack, which is called the masking. Yes.
Thank you.
Any more questions? I heard a voice. Sorry, Scott.
Naive question. Would, if you had generate a faulty signature, would it actually validate using the standard signature checking procedure?
You mean when I inject a fault?
Yes. Would it actually generate a signature which would actually validate?
No, it's not validate, but actually I checked that when we inject fault into the generator in the ideal, it outputs the signature like normally, but when we use that signatures with the verification, it doesn't validate.
Okay, so one obvious workaround would be whenever you generate a signature, just check to see if it validates.
Sorry.
One obvious way to address these attacks then would be whenever you generate a signature, you immediately validate it before you output it.
Yeah. It can be countered in this way.
I think we're now the coffee break time. Let's thanks Sean again and also all the speakers.